Hello everyone. Today we are going to be talking about how to solve intercept problems for 1D kinematics, right? So intercept problems, which is what I like to call them, are things where two objects, at least in 1D kinematics, two objects are moving in from opposite sides of a plane towards each other, right? So that could be anything from, let's say, two cars that are crashing into each other, let's say. So they're starting on opposite sides and then accelerating towards each other. It could be something that's being dropped and then something that's thrown up at the same time, and you're trying to figure out where they cross. In the example we're gonna do, it's two knights on horseback who are jousting, and they're gonna close the distance between them until they meet, and we're gonna want to figure out where exactly they are gonna meet, right? So I'm gonna pull up the problem here that we're gonna use. So this problem is number 35, I believe, from the physics textbook. And I'm going to do it here on the notes, right? So the problem says, and I recommend you screenshot it or freeze the video here so you can reference it later. In a historical movie, two knights on horseback start from rest 95 meters apart and ride directly towards each other to do battle. Sir George's acceleration, which has a magnitude of 0.233 meters per second squared, while Sir Alfred's has a magnitude of 0.365 meters per second squared. Relative to Sir George's starting point, where do the knights collide? Alright, so again, I recommend you copy down this problem before we start. Let me give you a second to do that. Alright, so I'm going to go to notes here. I'm going to open it up. Alright, so first thing you want to do is let's draw a diagram of what exactly is happening in this problem, right? So let's say we have this is our plane. This is what we're going to be talking about. And we're going to say that Sir George is going to start over here, and the other knight is going to start over here, right? And we know that this distance here is, according to the problem, 95 meters, right? So we know this is 95 meters, right? 95 meters. Alright? And then we know that Sir George's acceleration here is going to be 0.233, and Alfred's is going to be 0.365. So let's say acceleration equals 0.233, and this is 0.365. I apologize for the handwriting, but it's a little tough to write here on notes. Alright, so we know these two accelerations, right? And these are both in meters per second squared. I'm going to omit the units for simplicity, right? So what do we know? We know that the total distance they're going to cover is 95 meters, right? And because the accelerations are different, right? So this one here and this one here are different. They're not going to meet in the middle. They're going to meet skewed to one side. In fact, we know that because this one is bigger, Sir Alfred's is bigger, they're going to meet somewhere closer to George's side. So they're going to meet more on this side of the field, right? So what we want to say is, okay, let's call the distance, the total distance, d, is going to equal distance 1, which we're going to call x1. That's the distance that Sir George is going to travel, right? So Sir George is going this way. And then we're going to call distance 2, x2. That's Sir Alfred. So this is going to be x1, and this is going to be x2, right? 2. So you might notice something, though, and this is really here the key to the whole problem, and if you're getting it wrong, this here is probably actually why. You're going to notice that x1 and x2 are actually pointing in opposite directions. And that's very important for this problem. You have to consider that it doesn't really matter which one you pick, but you have to be consistent here. One of them has to be negative. Typically, we're going to call x2 here negative because it's pointing to the left, and we generally like the left as negative. But you have to say one of them is negative. Alright? It won't work otherwise. So what we're going to do is we're going to say, all right, let's call x2 negative. So then our equation's actually going to look like d equals x1 minus x2. All right? So now, what do we know? Let's move on. Well, we know that the distance, based on our kinematics equations, that x1 is going to equal v naught t, right, plus 1/2 acceleration, we're going to call it George's, t squared, right? And this we're going to cancel out because they're starting at rest. So x1 is just equal to 1/2 George's acceleration times t squared, right? So we're going to solve for t squared. So we're going to say, okay, t squared is equal to 2x1 over the acceleration from George, right? Then, now we're going to look at Alfred's motion, right? I'm going to draw a little dividing line here. So we know that x2, that's not what I want to do. Alright, sorry. x2 is going to be equal 1/2 at squared, right? And this calls Alfred t squared. But remember, here we know that x2 is going to be negative. So what we're going to do is we're actually going to substitute, when we go ahead and do this, x2. Because right now we have multiple unknowns. We have x1 and x2. We want to put it in terms of x1, right? Because that's what we're solving for. We're solving for how far away from George's initial position here, right, is the collision going to occur. So we're going to solve for x1. So we want to get rid of x2. And how do we do that? Well, what we're going to have to do is we're going to solve for it using this equation here, and we're going to solve for x2, and then we're going to get that x2 is equal to x1 minus d, and that's going to equal 1/2 a t squared. Right? Cool. And then we're going to plug in, we're going to solve for t squared here, so we're going to say t squared is going to equal 2 x1 minus d over the acceleration of Alfred, right? And now we have two t squared equations. We have this one, and we have this one. And of course, the two t squareds are going to be the same because t is going to be equal, right? So I'm going to scroll this down a little bit, right? So now we're going to set these two equal to each other. So we're going to set these equal to each other. And we're going to get that 2x1 over George's acceleration is equal to 2x1 minus d over this. And now we can just cross cancel the 2's, or cancel the 2's here pretty easily. And then we're going to get x1, and we're going to cross multiply here, times AA is equal to George's acceleration times x1 minus George's acceleration times t. And now we're going to solve for x1. Alright, so we're going to bring, I'm going to do this all in one step, but in reality we're going to bring this to the other side and then factor it out and divide. So what we're going to end up with is AA minus AG. There we go. Oops, I'm sorry. I apologize. That's not what I'm going to do it like this. So we're going to say x, so we just, because it's easier to read it in this format. This x1 is going to equal, so I'm going to bring this to the side, and then I'm going to say x1 is going to equal negative, right, because we still have this negative here, AG, so George's acceleration, times the distance, divided by, and then it's this factored term that we're going to have over here. It's going to be A minus AG, right? So that's going to be our final equation. And you might be wondering, why is it that we have this negative sign here, right? Right? Because our distance should be positive. So we're wondering, and we see here, oh, well, AA is actually bigger than AG, if we remember correctly. This was 0.3, and this was 0.2 here, right? So AA was 0.3, and this one was 0.2. So you might be wondering, why is it that there's a negative sign here if distance should be positive? Right? We are, in fact, solving for a distance. Well, the interesting thing is, remember, let me move this up. Alfred's acceleration is actually going to be negative. This term here is actually going to be negative, right? So when we plug in, we're going to say x1 is equal to, we're going to say, okay, negative George's acceleration, which is going to be 0.233, times the distance, which we said was 95, divided by, and when we do Alfred's acceleration, we have to factor in it. He's moving to the left, and he's speeding up. So his acceleration is actually going to be negative 0.365, and I did it red here just for effect. Right? Switch back to black. Minus George's acceleration, 0.365. Right? Multiple. Minus 0.233. Right. So then here, for x1, we're going to have negative 0.233 times 95 divided by this is going to be negative 568, and that should give you 37 meters. This should be your answer more or less, depending on how you round it. Now, remember, make sure on Wiley, a lot of the times the numbers are different for most people, so you might not have gotten this answer. Just make sure you followed the same steps to get there, right? So I'm going to scroll up for a second let's review where it's easy to go wrong in this problem. The first big place is here, I've circled it in red, is with this distance equation, right? So if you use the first one, d is equal to x1 plus x2, you're going to get it wrong, just because this distance, x2, has to be negative since we're moving in the left direction, right? So you have to use the one circled in red. And then here again, when you go to plug in the acceleration, make sure you use a negative acceleration for Alfred, because he's moving to the left, right? So this type of problem is not too difficult conceptually, but mathematically it can be a little bit challenging just because of the negative signs, so just watch out for that. That's it for this kind of problem.